Okay, thank you very much, and thank you for the invitation to present here. As I said, I'm Julian. This is going to be a brief history of how Walla is used for JavaScript. Now, Walla stands for the Watson Libraries for Analysis. It's meant to be a generic toolkit, really, for doing program analysis. And this is sort of talking about, this talk is going to be about why we started doing JavaScript in the first place, which isn't the reason that you probably may be thinking, and some of the research that we've been doing, although this isn't primarily a talk about any specific piece of research. So before I start, I should say that Walla for JavaScript was not created by me alone. There's a large number of colleagues you can see on the slide there, and you may notice the number of those colleagues, their affiliations are in parentheses. You may notice the number for whose affiliation is not IBM. So it's one way to think about it is Walla has been created by a distinguished collection of Watson alumni, and the Alumni Association being one of the most rapidly growing groups at IBM. So let's start with in the beginning. I just found a picture of the Big Bang, some physicists' conception of it. And the question is, why did Walla start with JavaScript? So what was going on in the origins? And they're kind of important. The origins actually have flavored quite a bit of the structure of Walla as you see now. William Faulkner said the past is never dead, it isn't even past. So originally, way back, Walla was a framework that was designed for analyzing Java bytecode. And it provided sort of core analysis functionality. You could build call graphs, you could do pointer analysis, control dependence, the kind of things you'd expect a compiler framework to be able to do. And its original purpose before JavaScript was it was used actually to support certain analyses in IBM WebSphere products, looking at analyzing how Java 2 Enterprise Edition was configured and it was actually for suggesting improvements. But while this was shipping, people at another division of IBM Tivoli, another piece of software group, had a need for analogous functionality for JavaScript. They looked and they said, you have call graphs, you have control dependence, we need those. But we don't have Java, we have JavaScript. And the first thought was, well, maybe we can just compile the JavaScript to Java. There are several tools that do that and analyze it. And the result is that doesn't work, right? Because you basically, what they really are is they're interpreters, right? They tokenize the JavaScript and they have an interpreter. Analyzing that doesn't work terribly well. So we ended up thinking we would need to build infrastructure, and we had a bunch of stuff already with Walla, and we were trying to reuse it. And I want to talk a little bit about what they wanted to do with JavaScript. They wanted to analyze monitoring scripts. And now Tivoli's, one of its products is IBM Tivoli monitoring, and it basically runs on your system, and it kind of says every once in a while, it wakes up and it says, has something crashed? Has it run out of memory? Has it rebooted recently? And it will send messages if these things happen. And what they wanted to do was provide tooling for migrating monitoring scripts written in JavaScript to a new model. Now let's just see. So this is due to, I was told I could reuse old slides and give old talks. I don't think people anticipated that that meant 10-year-old slides, but this is one of the things, this is basically a description of what we proposed to build for Tivoli in 2005, which is the origins of Walla for JavaScript. So the analysis was called Domo back then, don't ask, it's now Walla. IBM has a lot of lawyers, names have to be approved by lawyers. And it turns out there's some Japanese cartoon character named Domo, so you know, some way more important than program analysis. So this is the original analysis we had that was for Java. But we were going to generalize it. Don't worry about this bullet. That's very specific to the project, this particular project. But the plan was to build this scripting language front end for Walla. The idea was that it would be sort of provide generic stuff useful for people who are manipulating source language. If you have the ASTs and whatnot, and support for control, flow graph generation, and that sort of thing. And on top of that, we were going to build analysis for JavaScript. And then on top of that, there's this thing called the situation extraction tool. And what Tivoli wanted was they wanted to look at their old scripts written in JavaScript, run them through a magic tool, and get new scripts that are written for their new version of the Tivoli monitoring product that did not include JavaScript, because it had occurred to somebody that using JavaScript was unnecessary and probably not something that anybody particularly would have been doing if they'd planned it better. So this is what people tried to build. And let me just give you a flavor of what the extraction meant. So they were just using it as an ordinary scripting language. Right? There's nothing to do with the web here. This is not going to use a DOM. It's not going to use jQuery. It's not going to do anything that makes you really want to throw up. Well, it is, but there'll be different things. And they basically have this function called visitTree, which is just a random function in the JavaScript code that they're going to call. And basically what it does is it checks system state. And there are two things it can do. If there's an event, if something interesting happens, like say the machine had crashed recently, something like that, it will send an event. And for these events, it can attach data. For example, it could be looking at a machine and say, well, you know, you've been using a lot of memory recently. And it would then, and attaching the data might be, here's what fraction of your total system memory has been used, or something like that. And what they wanted to do was to use analysis to extract from the JavaScript code the declarative meaning of these things. What kinds of events is it sending, and why? What data is it attaching? So let me show you an example of the JavaScript code. This is the magic function, visitTree. And now what blue means, blue is data that's going to be attached to event, and green is the control condition under which an event gets raised. So let's just take a quick look. I won't go through it in great detail. First, we figure out how many web servers we have. If we have 0, we return something that basically says, I'm not interesting. Otherwise, for each server, we basically check web server availability. And if that's equal to not running, we're going to raise this event, Apache EV server stopped. Right? Basically, wake up, see if my servers are running. If they're not, panic and send a message to somebody. So it's not fundamentally, it's a simple thing to do, but it's all embedded in this JavaScript code. And what they wanted was a result that would look something like this. And this is the same, this is what we extracted. This is a dump of what we extracted from that particular program. So for example, this is going to send an event, server stopped. When? It's going to do it if your value, or it's going to basically get this primitive is web server availability. It takes the, we're going to basically check, we're going to read that, and then we are going to check whether or not it's equal to not running. And if so that's the condition under which we'll raise the event. And similarly down here, there's also some data we attach. We attach the name of we attach something called web server app proxy. These scripts do all kinds of weird stuff like that. They attach seemingly random constants and all kinds of stuff. So if you look at this, you say, well, what do we need? This is basically control dependence, right? When would I execute that send raise event? It's a control dependence. This is some data flow. So basically, that's essentially the level of functionality they needed. Basic compiler analysis stuff, which we had in Walla, and the purpose of originally creating Walla JavaScript was to enable this for Tivoli. So what happened? So that is why Walla JavaScript was born. And the current structure of the front end, you notice I had JavaScript, and then underneath that I had a scripting languages layer. That structure is still very much permeates the code. We use Mozilla Rhino for JavaScript now. And the script migration shipped an IBM Tivoli ITM 6.x product. It was based on Walla. And one thing to keep in mind here is if you look back at this function, we're only really interested in this one function, right? So there are more complex scripts, which won't fit on a slide, that use a couple of functions. But really, heavy-duty interprocedural analysis was not a focus. It was not necessary. So our relatively traditional, context insensitive 0 CFA kind of call graph, context insensitive, pretty basic stuff was fine. Now, so this is good. But as you can imagine, once this infrastructure existed, people began to think, maybe JavaScript is used in situations other than esoteric Tivoli monitoring products. Maybe somebody else uses JavaScript, and we could do some stuff there too. In particular, some people use JavaScript on the web. So then we would basically, so we have this infrastructure, right? We can start looking at web pages as well and do analysis for that. And this picture is meant to kind of give a flavor of the result of what happens if you try to apply relatively naive program analysis to the sort of JavaScript you find on the web. I mean, I think this is a mountain, and the mushroom cloud is really quite big. So why did people care? Well, many of you probably do online banking. In fact, most of us only bank pretty much online. If you go into a bank, they charge you money, and they annoy you, and they make you wait, and so on. So this is our interface to a bank these days. So this is what it would look like. But then there's this magic button called View Source. It looks more like this. This is also your bank, actually. This is actually a view source on the page I showed you just now. So, you know, everybody, you look at this line right here. Open, close, curly, paren, semicolon. What sort of a source code line is that? You know, if this is what your source code looks like, you can understand why the people who run banks are very worried about whether or not their code is doing anything reasonable. And so that is the purpose of, while the JavaScript technology was applied to web code. In fact, there's this product at IBM called IBM Security AppScan, which is about scanning. It's a bunch of different, it's a line of family of products, really. It scans websites, it scans source code. And in all these cases, the JavaScript is a big deal to them. And so it basically looks at the code, it tries to apply security rules to understand whether or not your code is doing something bad. And if it's doing something bad, it shows bugs to developers. So that's the idea. And again, we started with like, OK, that's easy, right? We're doing some data flow. So we have call graphs. We have pointer analysis. What could go wrong? Let's just try this. And the mushroom cloud perhaps suggests quite a few things did go wrong. But let's see what happened next. So traditional call graphs of the kind that we had built and were perfectly fine for the Tivoli use case, what does that do? Well, JavaScript makes it rather difficult. First thing, there are things we all know about, like the heavy use of eval and other forms of reflection, which just make life relatively tedious. But there's another issue. In JavaScript, many of the times when you reference an object, you do something with a first-class property name, which is this sort of format here, x.s. This is where s is now a constant, right? And then here, x bracket v in JavaScript. This is common v as a variable. It has to map to some kind of string. So this is what sort of traditional people who will tell you things like Anderson analysis is n cubed. They tend to be interested in this kind of thing. So what happens here? If I want to analyze this statement, now for every object that x might point to, I now need to figure out for that and every object that its s field might point to, those now have to contain everything that y might point to, right? Because I just assigned y into the field. Any field I might assign to now has to have everything I just assigned to it. And the analysis of Anderson depends on these two things are potentially bounded by the proportional to the size of the program. The larger the program I have, the more fields I might have, the more objects I might have. So this is n squared, and then the n cubed comes from the fact that the number of statements is also obviously proportional to program size. So I have n squared here times n statements gives me n cubed, which is what people use for the bound on Anderson. It's usually called an n cubed, which is already expensive, but you know it's not exponential, it's not undecidable, so in program analysis we're happy. But JavaScript actually makes things a whole lot worse, because now if v is a variable, there's now an additional dimension of variability, which is every field, every string to which v might refer is now one of the fields to which I might assign. So these two are the same, but now I have another dimension of the number of strings. And again, that's proportional to program size, right? Just the sheer size of the text, I can write more strings. So this is actually makes Anderson's n to the fourth. So you've really made the asymptotic complexity of basic program analysis more difficult, in addition to all the other problems that JavaScript causes. And this is from an eCube 12, I believe, paper. So that was a disconcerting result, but you think, you know, there's asymptotic complexity, and then there's what happens when you actually run stuff. Maybe we don't care. Well, turns out you do care, unfortunately. So I'm going to show you a fragment of code that's very familiar to people who do program analysis for JavaScript, because it's what keeps us all up at night or puts us to sleep or something. It's called the extend function. This is actually a somewhat simplified version of code that's in jQuery. So let's look at this ext method. What does it do? this idiom for var p in obj is iterated. P now iterates across every property name that's defined in obj. So if I had 3 properties, this would iterate 3 times. And then I'm essentially taking this data in obj sub p, and I'm assigning it into this other variable, jQuery.fn, don't worry about that, sub p. So I'm basically copying from obj into this other jQuery.fn object. Now, that's fine. That's all very well. But if you think about doing any kind of flow insensitive analysis, the question you have to ask is, what does obj point to? Okay, I have some points to set for obj. What does p point to? Well, p points to every field that's bound in obj. So now what does obj sub p point to? Well, it points to some value that's stored in some field of obj. And then what does this assign? This points to any field of jQuery.fn that's in this, that p might point to. So essentially what I'm doing is I'm basically taking every value in every field of p, of obj, and copying it into every field of fn. And so I'm basically I'm massively polluting my points to analysis if I do flow insensitive every time I go here. And so what that means is it's not only terrible in theory when you try to do this with jQuery and JavaScript, it's terrible in practice too. Essentially what happens is either your analysis doesn't finish or you get no useful information, or both, usually both. So the first thing we tried to do to fix this is to say, well, okay, so that's a problem, but what's really going on semantically is that each loop iteration is operating on a different value of p. Our problem here is that we have one representation of obj sub p. And what we actually need is a separate analysis of the assignment for each possible value of p. And that is the sort of thing you do with context sensitivity. And in particular, what we want really is context sensitivity applied to the loop body, where the context is determined by the abstract objects that might be here in p. And that's effectively what we did. And I have an illustration of what that effectively does to the code. So the code was actually implemented using normal context sensitivity and some hackish code to rewrite ASTs. But effectively, what you really want is this. So if p is x, my statement does this, right? jQuery sub x equals obj sub x. Well, it's dot fn, but whatever. This is just truncated a bit to fit on the slide. If it's y, then actually this should be y, I suppose. But the point is that for each value, let's just look at this one. For each value x, now I'm copying x. If I analyze it that way, now I avoid the pollution because I understand the properties from obj of x go to jQuery sub x, but the properties of obj sub x don't go to jQuery sub y. So that's, in a nutshell, what correlation tracking did. And that was the first thing we tried to do to make the analysis a little bit better. And so now the question is, how does that work? So this work, by the way, is all from an eCoop 2012 paper. So what happened here? Well, the table here is showing a couple of things. If you look at baseline and correlations of what you might expect. So baseline is the analysis without this special analysis for the loops. And correlations, we call the analysis correlation tracking, is with that analysis for loops. And for now, just look at the columns which say minus and ignore the columns that say plus for now. If you look at those, the story is it's not bad at all. Everything kind of blew up, and now everything's pretty good. So we're done, right? We fixed it. We rock. You know, we took this problem and we applied context sensitivity, and everything's good. But now, what does the plus mean? Would be an obvious question at this point. And plus and minus mean without modeling of call and apply. So call and apply, it's effectively other forms of reflection and indirect first-class use of functions in JavaScript. And if you put in plus, everything's a disaster before. And unfortunately, if you put in plus, not everything works even with correlation tracking. So correlation tracking has helped, but there are clearly other things going on here that further complicate the analysis and make it very difficult. And the framework-based code was beyond the state of the art. And the state of the art has improved in the meantime, but it's still the case that if you take an arbitrary, ugly piece of jQuery code and based JavaScript code and throw it at a static analysis, your static analysis is very unlikely to be happy. So that was unfortunate. And given that the point of this code is to power IBM products, well, one of the purposes, that analyze web pages, this is especially unfortunate when you consider that practically every web page uses jQuery. So that was unfortunate. So what did we do next? We went to a famous philosopher from the Peanuts comic strip called Linus Van Pelt. And he had this lovely saying, no problem is so big or so complicated that it can't be run away from. And so that, we decided that is what we need to do. We need to take this advice. So how do you run away from this kind of problem? And what way you run away from it for us is a technique called approximate call graphs, and let me show you what that is. So let's go back to jQuery for extend function. This is the cause of so much grief. Let's take a look at it. What's going on here? One thing, what we observed was that what this statement actually does depends very much on the abstraction you use to represent objects at compile time. Let's say you have an abstraction where all objects that ever get allocated in the program, every last one of them, map to effectively the same abstract object, right? Now, leave aside for a moment the fact that this is likely to be fairly imprecise. Let's not worry about that yet. What does this statement do for the static analysis? It's now a no-op. Why is it a no-op? Because every value of p has to be something. And I only have one field, one points to set in the entire program for every field with the same name. So this is going to be assigning from some field, some abstract objects field, to the same one, because one thing I know for sure is that p is the same on both sides of that assignment. I don't know what it is. But because I only have one abstract object, this is a no-op. And we know how to compile and analyze no-ops. We do nothing. And that tends to be, in this case, a lot better than trying to do something. So this requires we imprecisely merge properties for each name, and because it makes copying fields a no-op. And another side benefit is when you look up a field now, we no longer need pointer analysis because there's only one. If someone says p, we know what p is. There's only one in the whole program. So we're not going to do much pointer analysis either. So that's the good side. There's a lot of stuff. We'll just ignore all the things that cause us trouble. We won't do pointer analysis. So that is going to make things a little bit easier for us. But now, there are some issues with this because the statement that we're ignoring is not, in fact, a no-op. For instance, suppose you had a piece of code like this, and now you may look at these pieces of code and think, oh my God, this is like a contrived piece of code that no one would write. Sadly, all of these are taken from actually relatively old versions of jQuery by now, and jQuery has in fact become even worse over time. So what happens? We have an array with 2 strings in it. We now loop through the array. We take the name from the array, we prepend outer to it to build a new string, and we assign to that field. Now, the way we're dealing with indirect property rights, these indirect property rights, is we're ignoring them. So we are not going to, we're going to ignore this. We're going to assume it's some weird, horrible extend pattern, and we're just going to ignore it. And so we're going to miss these functions entirely. Some functions are only written in such accesses. You find that this is an example. Outer width and outer height are not going to be written anywhere as far as we're concerned, because they're only written in these indirect accesses that we're ignoring. And field-based analysis is imprecise for some idioms as well. Anyone who does object-oriented overriding, right? The whole point is in a superclass I assign f to be one thing, and in a subclass, I make f some other function. That's how I do virtual method overriding in JavaScript. And for us, we're just going to assume that everybody might have any of them. So we're giving up on trying to do any kind of disambiguation of object-oriented dispatch. So there are some pretty significant costs to this as well. The only saving grace here is that, fortunately, JavaScript's idioms make object-oriented development so tedious and painful that people do less of it. So that helps. But if they do any, we're not going to do anything very precise. So then this brings up two issues, though. We're doing things that are unsound, because here we're going to miss things. And we're doing things that are imprecise. So we're going to get a call graph that has some edges. And hopefully, the edges it has bear some resemblance to the actual edges that you might see running the program. But there's no guarantee of that. We're going to miss stuff. We're going to have extra stuff. So empirically, how bad is this? So let's see. The first thing we measured is call graph precision. And this is something that a compiler person would traditionally be, an analysis person would traditionally be interested in, which is, of the edges I think are in the call graph, how many really are possible? And as with much analysis research, we're approximating what might be possible with runtime measurements, dynamic measurements, because those exist. It may not, there may be other runs that could generate more edges, but you run as best you can, you try and get as much as you can, you play with an app for a while, stuff like that. So basically what we're looking at is the fraction of the static edges found in the dynamic call graph. Of the edges we think are possible, what fraction did we see? And of course there's noise, it's variable like most graphs, but on the other hand, given the extent to which we're just completely ignoring lots of property rights, it's not as bad as you might expect. Because remember, the bars look kind of low, but the origin here is 60%. So it's between 60 and above 90%. So we found, the majority of the call graph in all cases. And in some cases, we found almost all of it. Those presumably are programs that do relatively little that depends on dynamic property rights only. Now, one thing to keep in mind, there's optimistic versus pessimistic, and it's hard to see the pessimistic bars anyway, so maybe I'll just ignore it. But basically, what pessimistic is a way of cheating even more, of even certain propagations, interprocedural propagations, we're just going to decide not to follow because it's cheaper not to. So that will tend to cause us to miss more stuff. So precision is lower in the optimistic. So that's sort of what's going on there. We're finding fewer edges, we're following fewer things. So we are going to produce a subset of the edges. So precision in this case goes up because we're doing less propagation, we're getting less noise. So that's precision. Now another thing, and this is a little weird because traditionally when you build a call graph, you wonder how precise it is. Recall is how much do we miss? And if you think about, and if you have a mindset that says call graph construction is conservative, recall should always be 100%, right? If you miss something, that's a bug. For us, if you miss something, it's because we couldn't be bothered to keep track of it, or we don't know how. So this is the fraction of dynamic edges found in the static graph. So that says if I found what fraction of the edges that I really see did static analysis think I might be able to see. And again, the unsoundness is actually limited, given how much stuff we're ignoring. And again, notice again, 60% is the origin, and recall is up. Recall is high, right? It's greater than or equal to 80% mostly. And in this case, optimistic versus pessimistic goes the other way around. They're almost the same by and large, but pessimistic is going to be lower because it finds strictly fewer edges. So it's going to miss more stuff. So this is approximate. You can see from these results we miss things, but we don't actually miss a lot, usually, except when we do, but that's another story. So what does that mean? So I'm going to say a little bit. So this is what we've built. Another question is, so what do we actually ship? And the products that we focus on now with Walla JavaScript are IBM AppScan, IBM Security AppScan, and this is the code. These are the products that look at web pages. either from a developer who's writing them or from a testing tool applied to a website. And what we actually ship is the approximate analysis, is the field-based approximate thing I just talked about. And the reason we ship this one is this is the one that terminates. Right? This is the one that doesn't have the problems with jQuery, things like that. And since almost all modern web apps use all kinds of frameworks, this is really the only thing we have that works. Now, even there, we use timeouts, we use heuristics, we have all kinds of hacks that we throw in for the purpose of making the analysis results look a little bit more like what the test cases and customers want. But as you can imagine, it's not entirely satisfactory to build security products whose way of analyzing code is to pretend that significant portions of it don't exist. Since then, ideally, right, it would be better if we could analyze more of the code. People have, I think, more or less given up on the idea of a security tool as a verification tool. Customers do not expect that. They know perfectly well that the analysis is going to do all kinds of stuff. What they're more interested in, can you show us some issues that we can fix, make our code incrementally less bad than it was before? But despite that, because we are also researchers, there's a couple of forms of ongoing work to improve this. So one of them is using symbolic analysis. So imagine your approximate call graph with all kinds of junk in it has given you some data flow that you think is going from, say, user input to a write to the DOM. One way to try and convince yourself that this is a real issue instead of the result of the analysis making stuff up is you try to figure out whether there's an actual string that you could imagine flowing through there that follows the program logic. And you could try to build a concrete one using some sort of symbolic execution approach. So that's one strategy that there's ongoing work. And the other ongoing work is exploring models of JavaScript frameworks. So at one point, even in Java, what has happened with, for example, J2EE, is you cannot actually analyze J2EE. It's all reflective. It's all calling the bytecode compiler, loading classes, jumping to stuff, doing random things. And what actually has been done, and this is actually an IBM product called Framework for Frameworks, is there's code for allowing customers to model the behavior of the frameworks they use to improve the quality of their analysis. There is some, you can read about Framework for Frameworks in an OOPS paper. It's not germane here since it's not applied to JavaScript yet, but ultimately that is another direction. We are sort of actively exploring how could you do framework modeling in a flexible way. In JavaScript, there are hundreds of frameworks. There are new ones every year. They get worse and worse. But in some sense, the overall message, to my mind, is this is splash I wanted to say something about sort of how this relates to our friends in the product divisions. And the fact that we use the word friends already seems like a good sign. So IBM products, the whole point, right? While the JavaScript actually started because people in Tivoli asked for it. And they were not doing anything on the web. And now further call graph construction is driven by, a lot of it's been driven by demand from people in AppScan. So as you can imagine, as soon as they started analyzing real web pages, they came back to us and said that doesn't work. And that's where correlation tracking came from. It's where the field-based work came from. And there's ongoing support for further analysis research because, I don't think any of us feel that the approximate analysis we have now is entirely satisfactory. But it also goes the other way because we drive the products as well. We are pushing. So for example, one of the things that's been done, we have this scripting language framework for Walla. One of the things we've started to look at is analysis of Apple's Swift language, which is, it's IBM makes a big deal of its alliance with Apple. And one of the things we're hoping is that the level of expertise at Watson in terms of programming languages and optimization technology is something we could maybe we could use. And then Framework for Frameworks is this thing that's not germane to JavaScript at the moment, but it basically is allows customers to model complex frameworks. And actually, IBM even will send, if you're a big customer and you're going to buy AppScan, IBM will send customer engineers to your site. They will look at your code, they will understand what frameworks you have, and they will use research-developed tools for building models for those frameworks. And the plan is to extend that to JavaScript as well. And again, this is all of this work has been done with sort of a collaboration between developers and people in the product division, and especially in AppScan, and those of us in the research division who don't think of ourselves as developers but get pulled in that direction at times. Okay, and with that, I thank you very much. That's all I have.